The class is starting. Welcome back, folks. Well, we do intend to go over the exams at the start of class today, so passing back exams is not entirely inappropriate. Anyone not get a copy of their exam? Okay. So welcome back, folks. We had our second exam, and if you're curious about the statistics on that exam, the exam 2 average was equal to 71.8%, and the maximum score was equal to 92.5%. So those are some minimal summary statistics, but those are the summary statistics on the second exam. Any questions about it? Okay, it was definitely a tougher exam. I believe exam 1 had an average in the mid to upper 80s, and the maximum score was something like 99.5, if I remember correctly. So this one was a bit rough. So if you were not completely happy with your exam score, we could have an extra credit deal towards the end of the semester. So at the very end of the semester, which is really not that far away, finals week, if your final exam score is larger than your lowest of exam 1 through 3 scores, I would do a full replacement. So if, for example, you're not completely happy with your exam 2 score, but you got, say, 98% on your final exam, that would be your new exam 2 score at the very end of the semester. So that one bad exam shouldn't really dictate a drop of multiple letter grades. But any questions about that? Okay, I'll add that as a comment down here on the finals week, just so that it's something in writing, which is always good. And you're always welcome to ask questions about it later on. So let's see, where are we at so far? So far we have assignment 8 that's being slowly built up. We do not have an assignment that's due this week, since the section of 11.2 was really just optional problems. That's why it's 7.5 for the assignment, not a full-on new assignment. But despite that, these are still really important problems. We'll find that they're still useful when we go to the third exam, because we have 2 important tests, the geometric series test, and more importantly, the test for divergence. So are there any questions folks would like to discuss on that problem set? Okay, and maybe just for a sake of reminder of what we did before, let's go down to the week of April 1st through April 7th. That's going to be a week before our third exam. What we're going to get into is we're going to have series is a redundant word there. We'll have a set of various tests to determine when series converge and when series diverge. And so this is going to become a very, very helpful flowchart. So far what we have is the test for divergence is a very specific test that can work in certain situations. And we also have the geometric series test is what we've done so far. Whether things converge or diverge is dependent on the thing in the yellow box. This implies convergence. And this is really the only formula where we can determine the actual exact sum in terms of convergence. For everything else, we'll just say it either converges or diverges. That's also a very helpful table or flowchart, because if you did go to use the test for divergence, it tells us do this check. If the limit is 0 and you say yes, that's the case, it directs you to something else, because then that test has failed and it tells you try a different test. Their next recommendation is do the p-series test. If it doesn't have this form, then you would say no and consider it as a geometric series and then just continue on down the line. Of course, we want more familiarity so that we're not using the flowchart in that exact order every single time. That could take a while. But we've also have, for a couple new tests, the p-series test we'll discuss today and in next class. And way down below is the integral test, which is also what we'll discuss today as well. The integral test is kind of nasty, so it's nice that it's on the very bottom. That's the test of very last resort. That we'll discuss today. But any questions about that so far? Okay, so that's where we're going. And this is really the reason Chapter 11 becomes a pretty interesting chapter. It's because we have many, many tests working at the very exact same time. On the third exam, the only things I would not emphasize are the geometric series and telescoping series, mainly because those are things that we covered on the second exam. But any questions then before we continue? Okay, let's start our work then for section 11.3. We'll also have 11.4 due to this on this new assignment as well. So in 11.3, we're doing yet a new test. So far we have the test for divergence. The second test is going to be the geometric series test. And our third test for the entire chapter 11 is now the integral test. So we'll state that next. Any questions so far, however? Okay, so let's start with a brand new test, the integral test. And this is the situation. We want to once again test the following. So consider the series summation as I goes from 1 to n of a sub n. So if we have this series, and it's not, say, a p-series, it's not a geometric series, and the test for divergence fails, we sometimes will use the integral test next, if it seems like the appropriate next thing to do. To do that, we let f be a function for which f of x, or rather f of n, will be equal to a sub n. So far what we have is, we have a series where we're adding infinitely many different terms in a sequence, but we're also defining a continuous function so that if we put in an index n, it matches the exact value of the nth term of the sequence. So we're taking a series of dots, the sequence itself, and considering its continuous analog, the function f. Mainly because if we want to integrate something, as this implies, we need a continuous function to make that happen. So next are the hypotheses about that function f. Questions so far? Okay, so here we can say if f satisfies first condition, f is continuous on the domain from 1 to infinity. Where 1 through infinity comes from is where the index is starting. Oh, sorry, this should have been n equals 1 to infinity. Apologies to those working in pen. That should have been n there circled and infinity on the top, so that we have infinitely many terms we're actually adding. Then, if f is continuous on from 1 to infinity, where n starts, next, f is a positive function on 1 to infinity. This is just a way to say f of x is bigger than or equal to 0 on this specific domain, which also forces the terms of the sequence to all be non-negative. And one more, f is decreasing on that same domain, once again, from 1 to infinity. Then we have a conclusion. But if we're going to use the integral test, we have to check 1 through 3. If one of those fails, any single one of them, then the test would not apply. So say, for example, if the function has a negative value, if f at 3 is -6, then the entire test cannot be used. Possibly it could be used in conjunction with something else, but that would be kind of rare to do. So first things first, we check 1 through the 3 holds, and here's the conclusion of the test. Then the series, this thing, we're trying to add infinitely many terms and see if a number can be ascribed to it. So the series, summation as n goes from 1 to infinity, of a sub n, converges if and only if this thing, the definite integral from 1 to infinity, it's now an improper integral of f of x dx converges. So that's the statement of the integral test. It really says quite a lot at once, but I think what we should do before we apply it is draw a picture to explain why those two things should be related. Why, if the improper integral converges, must the series itself converge at the same time? But first, any questions about the statement of the theorem, the integral test? Okay, so next, let's try to illustrate what this test is trying to say by doing a graph of the sequence. So let's suppose the definite integral from 1 to infinity of f of x dx converges. So let's draw graphically what that situation would imply. It would mean, if we look at this graph, let's maybe make it look like this. We need to focus on quadrant 1 because the function should be positive. It'll satisfy 1 through 3 there. So we'll say this is starting at 1, 2, 3 through 4, and so on. So if this converges, then summation as n goes from 1 to infinity of a sub n must converge. So that's part of the statement of the integral test so far. So here we'll draw a picture where this does actually converge. But first, let's look at the summation as n goes from 1 to infinity of a sub n. This series here, n goes from 1 to infinity, summation of a sub n. It's really just a shorthand to say we're taking a1 plus a2 plus a3 plus a4 and so on, infinitely many terms, and trying to add them up to see if we get a value. That's really no different than this. In fact, the sign here for the integral sign is just an elongated s to refer to summation. So let's plot first the sequence, a1, a2, and so on. Let's say that a1 is maybe here. The second part of the condition says that, well, the third part, the function f is decreasing, and the function has to go through this point. Also has to go through the next point, so the point should be slightly lower as we go. So that's what the first 4 terms of the sequence, which is commas instead of pluses, would look like. Then the graph of f is the continuous version of those points, and it would look about like this. So this is f of x. That look all right so far to folks? Okay, so we're saying that this value here converges. So from 1 to infinity, the area under the curve should be some finite number. But also, if we look at this, a sub 1 is really this. Does that make what sense why? If we drop a rectangle right here, then the area of this rectangle would be a sub 1 itself. Reason being is, recall that f of 1 should be a sub 1. That was our preamble right here. The function values matches the sequence values. So if we put here a height of a1, take 1, the base, times the height a1, that would be a total area of a1 itself. So you could take a new point of view on a series like this and say the series is really just trying to add up infinitely many different rectangles, which are supposed to have the exact same width, but that was the best I could do on this drawing. Should have made that a little bit wider. So the next rectangle would be a2, then a3, then finally a4. There's infinitely many more, so I'll just do dots to express that. So that would be a1 through a4 plus infinitely many more rectangles. Yeah?
Do you always want the rectangles from the right?
Not always. Depends on convergence or divergence.
Okay.
But notice that if I made my rectangle, let's say we looked at a sub 2, I made it go like this instead, it would be the exact same area. But the interpretation would be possibly different. So if I changed to suppose this diverges, I would draw it slightly differently. What are the questions so far with that picture? Okay, so this is what the integral test is then trying to say. We have that the definite integral from 1 to infinity of f of x dx is equal to some number I'll call L. This is just due to the convergence. I used L for limit because it reminds us that this has to be converted to a limit itself. Then this thing is going to be bigger than, possibly equal to, but if you went strictly bigger than, then that's going to be most of the cases. Let's go with this direction. This should be bigger than or equal to the series, as n goes from 1 to infinity, of a sub n. Just because the series is just taking the rectangles, but the improper integral is also taking on all of this white space that's missing. So there's extra area not accounted for. Does that make sense so far? Okay, then the second portion of this stuff is condition 2 tells us f is a positive function. Well, because f is positive and these values match the function values, this is bigger than 0. So we have that the series is some value bigger than 0. It cannot be arbitrarily large negative, but it's smaller than something that converges. Would you folks agree that this must then imply this converges to some finite number? Yeah, it ought to be the case. Where if this was infinity, if it diverged, then this would be the wrong conclusion. So we do have to be careful, but that's the picture of convergence. Should we try divergence quickly, just to compare? Okay, so let's do next a quick sketch of the second situation, where we can say, suppose the definite integral from 1 to infinity of f of x dx diverges. Then, this test was telling us, due to the if and only if one part fails, then the other part must also fail. So we said, if this diverges, we can then conclude the series itself must diverge as well. So divergence of the improper integral says then, the summation as n goes from 1 to infinity of a sub n must also diverge. And this is very provable, but I think a picture is sometimes worth more than the proof. So let's look at what the picture should be in this situation. Any questions first? Okay, so I want to start with the fact that this diverges. It means my curve, this time, let's call this a 1, try to get a better scale this time, 2, 3, 4. It might look something about like this. The points still have to be always positive to match the conditions 1 through 3. They have to be decreasing because the function is decreasing. So it looks similar on the very beginning. The difference this time is if we want to write this out, the points shouldn't be decreasing very fast. And the curve, because the function f of x, improper integral from 1 to infinity, is divergent, it wouldn't decrease very fast as well. So we have that in this situation, if we make a rectangle that goes, we could do this again and call this a sub 1, but notice if we go over this way, then this would be the value of a sub 1. And it's this time an overestimate in terms of areas, because now we have area above the curve in this interpretation. Then we can take this point, call this a sub 2. Finally, this would be, say, a sub 3. And let's add just one more. From this point, this would be a sub 4. So that's the sketch so far. This time, the first 4 terms of this series has more area than the definite integral from 1 to 4. And this would carry on. We can say for all n bigger than 1, the definite integral from 1 to infinity, or uppercase n, of f of x dx is always going to be less than summation as lowercase n goes from 1 to uppercase N, the summation of the sequence's terms a sub n. So this inequality here is really just what is stated in the graph. Does that make sense so far? Okay, so in our graph here, this would have been the uppercase N. But if this holds for all n, and if this is diverging, we have this is always larger than something that is becoming divergent itself. It implies this diverges altogether. Since the terms of the series, or the terms of the sequence when added together, gives these partial sums, which are always exceeding something that diverges. So that forces the series itself to diverge at the same time. So that's the logic of how a proof should go of the integral test, and the reasons we have the 3 conditions. First condition is so we can take an integral. Second condition is to make these pictures come out just right with the correct conclusions. Any questions about them so far? Okay, what we ought to do next is let's practice using this test with some specific series where it's really well designed for. Any questions at all then before we give it a try? Okay, so let's give some instructions on these next problems that says determine the convergence or divergence of the following series. And for our first one for today, let's go for, how about the summation as n goes from, let's make it be 1 to infinity of 1 over n plus 3. So that's a series we would like to test. One thing we should be really careful of whenever we're testing series for convergence divergence is that we do know something specific about one series. The harmonic series is a summation as n goes from 1 to infinity of 1 over n, and it is divergent. That's a T there. So we do know the harmonic series diverges. We refer to a proof in the book to explain that, and we can also prove that with the integral test if we would really like to. And if we look at that one over there, would you folks agree it's similar to the harmonic series? In fact, very, very similar, and we'll have very other tests that allow us to test this in a much more efficient way. But as it stands, with what we know so far, as n goes from 1 to infinity of 1 over n plus 3, this is not the harmonic series. So instead of worrying about re-indexing things to try to make it look similar, that is something we can do in some cases, but not all cases, we're going to just use the integral test. So although it's very similar to the harmonic series, we can't immediately quote that it is divergent because it is a harmonic series, because it really is not exactly that harmonic series. It's close, and if you make it 1 over n, then it would be. But instead, we're going to test this using the integral test, because it's also not a geometric series as well. Any questions then before we begin? Okay, so if we're going to use the integral test, this is how that we should proceed. We'll let f of x be equal to 1 divided by x plus 3. So that takes care of this portion right here. We have to come up with a function that's continuous, positive, and decreasing. And to do that, we really just take the formula for the nth term of the sequence and take its continuous analog. Call it a variable x, so that f of x is equal to 1 over x instead of an n plus 3. Now we have to check 1 through 3. But first, would you folks agree that's a continuous function? Kind of depends, right? Because we can't put negative 3 in there for sure. We would be divided by 0, so there is a vertical asymptote, which is a point of discontinuity. However, the thing we have to check for continuity on is on a specific domain, 1 through infinity, where this is starting at 1 itself, producing this value. If we were starting at, say, 5 instead, we're allowed to change this to 5 as well, and check that it's continuous on the appropriate domain. So at 1 to infinity, this, notice, never encounters a vertical asymptote. Its one and only is at negative 3. So we can say, first, f is continuous on the domain from 1 to infinity, since its discontinuity is at x equals negative 3. So we've sidestepped the problem. Then we go on to the second portion. Would folks agree that the function is positive? Again, that depends, right? Because if you take this as a function and calculate maybe f at negative 4, you would get 1 over negative 4 plus 3, which is negative 1. So the function f, once again, is not a positive function. It has a negative output. But we're only concerned about the domain 1 through infinity. On that domain, if I'm only allowed to put positive values in for x, we would only get positive outputs. So we can say, 2, since 1 over x plus 3 is bigger than 0 for x bigger than 1, f is positive on the domain from 1 to infinity. So once again, we're lucky. If we start at 1 and go to infinity, it's continuous and a positive function, and we'll check part 3 whether it's decreasing. Any questions so far to that stage? Okay, there are tricks to determine if the function is increasing, decreasing. You could, for example, say that if f of x and compare it to f of x plus 1, if I go 1 larger and I say that f of x was the bigger value, that would be decreasing. So on one hand, we could prove that as an inequality. But on the other hand, if you looked at 1 over x plus 3, what's another way you could argue the function is definitely decreasing? Sorry, say again?
The limit,
Yeah, the limit, what would its value be?
it's getting closer and closer to zero.
Exactly, so the value of the limit is 0. It starts off at positive when we plug in 1. We get positive 1/4. And in the limit, we're approaching 0. That implies the whole thing should be decreasing for sure. Would you folks agree with that? Okay, there's other options you could take. I like that option. You could also say if f prime at x is less than or equal to 0, then f is decreasing. So you could use the first derivative test for increasing, decreasing from calculus 1. Or let's just say, let's go with the option you mentioned. We just can see from the form of the function that this values get smaller and smaller. So as x gets larger and larger, one over x plus 3, this would just get smaller and smaller, and that's our definition for decreasing. 1 over x plus 3 gets smaller and smaller. So f is decreasing. Or just write DEC for decreasing. I ran out of space. So far, this is the work of the integral test, and possibly you've been convinced this is the worst test. Not because it's not valuable, it's valuable to mathematics at large, but in the situation of if we're trying to converge or determine convergence divergence, there are different ways to do this one once we go to the later sections. And using this as an integral test, although it's powerful, it gets the job done, there is a tremendous amount of work to do. Your first step is to verify it meets conditions 1 through 3, like we've done. The next step is to look at the improper integral from 1 to infinity. If that converges, then the series would converge. And if this diverges, then the series would diverge. So we start by checking the conditions, 1 through 3. Now we'll do the improper integral next. Any questions so far? Okay, so once we're satisfied that we meet the requirements of the theorem, we now go all the way back to section, I believe it was 7.8, and look at improper integrals. So next step is we need to determine convergence slash divergence of the improper integral from 1 to infinity of f of x dx. So let's do that very next. So this can be rewritten as, next we take a limit as a parameter t goes into infinity of 1 to t, the function f at x, which was 1 over x plus 3 dx. So that's the limit that we would evaluate. We need a new parameter t because the fundamental theorem of calculus part 2 does not apply with an infinity. But it would apply with a parameter t, which is any real number larger than 1. So next, we can say that this is equal to the limit as t goes to infinity. We need an antiderivative of 1 over x plus 3. Anyone see what that antiderivative should be?
L at x plus 3.
Exactly, yes. If we have something in the denominator to power 1, then that's going to involve a natural log. It'd be x plus 3, and we should check in the chain rule if this would be a problem with the plus 3. However, the derivative, this would be our check, d dx of the natural log of absolute value x plus 3 would work out this way. Absolute value x plus 3 produces an x plus 3 without absolute values. It takes some algebra to prove that, but that would be the process so far. We multiply by the derivative of x plus 3, which is a 1. So that says, even with checking the chain rule, we hit the right target, 1 over x plus 3. So we've got the right thing here, which we'll evaluate from 1 to t. And notice that in this specific situation, that if you just use parentheses, you're actually okay, because the value, the largest or smallest value we're putting in is a 1, and so the absolute value of 4 would still be 4. So if you drop to your absolute values here, that'd be okay. But if you're being careful, because in some situations you have to be, that'd be the best answer. Other questions so far? Okay, so after we find the antiderivative, the very next step with improper integrals is we just evaluate. So it's still the limit as t goes off to infinity let's go with parentheses. We'll input the parameter t and write natural log of t plus 3. I'll drop the absolute value at this stage since everything is positive, minus the natural log of 4. So that's the evaluation for natural log x plus 3. Then we just take the limit as t goes to infinity. But the natural logarithm function, although it grows tremendously slowly, this will diverge to infinity as t approaches infinity itself. And the constant that we're subtracting won't make a bit of difference. So we can say that this limit is infinity, and the improper integral then diverges. Any questions to that step? That's a bit of a throwback problem for feels like a very long time ago. So improper integral type 1 would be revisited on these types of problems, which means it's something we should be prepared for on the third exam whenever we use the integral test. So the next thing to do is the conclusion. For the conclusion, you should mention the name of the test you're using. I mean, it's pretty clear what the test is, but I should need to know that you know which test is being used. Also, it's the best practice to say, since when we have many tests, it's good to know which one we actually used when we refer back. So your conclusion should have the following features. It should say, by the integral test, so name the test that you used, we can say the series summation as n goes from 1 to infinity of a sub n, which is 1 over n plus 3. What would you say should happen to that series by all of this work?
Diverges.
It must diverge. So that's the conclusion so far. Really, a lot of the work is just writing out all the details, checking the conditions, doing the improper integral. And if I said converges here, we could conclude by the same test, convergence on the last line. And if the improper integral diverges, we get divergence for the series like we just have. So that's how the test works. Any questions about it? Yes?
Do you want us to write the specific problem, or can we just say like a sub n?
A sub n would just be fine, yeah. So if you said something like this, actually just because you've mentioned the series, I think that's possibly specific enough. But a better shorthand would be something like that. You can even suppress n goes from 1 to infinity. It would be implied. Other questions with that problem? So that's the wild world of the integral test. One thing I do if I'm doing an integral test problem on, say, exam 3, the instructions would say, test for convergence divergence using the integral test. Mainly because it's something we should be tested on. And also it's meant to be a hint that none of the other problems at integral test would be a wise choice. So that we're not bogged down on using the integral test on too many things, just because it takes way too long. So we usually expect exactly one problem like this on the third exam. And the rest of the problems, there will be faster ways to get through it. But since it's a new test, should we try it again? Let's try this with a different kind of series. Same instructions, determine the convergence or divergence of something else. This one goes, well, this is the wrong section. That didn't seem right. Let's try something from the correct section. This one goes summation as n goes from 5 to infinity of n divided by n squared minus 4 to the power of 3/2. So this is a problem where the test we're about to use is possibly a decent idea. Still, we might find a faster way to do this one, but again, we're just trying to practice the test. One thing that's a little suspicious is that we're starting at 5. That's just so we can skip over a discontinuity. I mean, we could have started at 3, but we decided start specifically at 5. The changes it makes are, it feels like maybe the theorem does not apply any longer, but in fact, the theorem can be restated in infinitely many different ways. If there's a 5 here on the lower end of the index, we convert to 5 to infinity on all of the statements of the intervals. So as long as there's some number beyond which 1 through 3 holds, then the integral test can be used. Does that make sense so far? Okay, then let's do the next portion. We'll say let f of x this time be equal to x divided by x squared minus 4 to the power of 3/2. And we have to check conditions 1 through 3. It is tedious, but it is what it is. And it's good to know that if you grabbed a problem out in the wild, say later on in this book, you could tell right away whether or not the integral test is going to be worth anything at all, because there's going to be plenty of functions where it just does not apply. So say, for example, if I do something like this, then that's now possibly an increasing function, depending on the appropriate power, and the whole test would not work any longer. But for this particular case, we can first say, for part 1, then f is continuous. It's continuous because we have a ratio of continuous functions. X in the numerator is continuous. The 3/2 power of x squared minus 4 is continuous. But more critically, f is continuous since is continuous on 5 to infinity, since the discontinuity is at x equals 2 specifically. That's when we would encounter a vertical asymptote. Some of the problems are just continuous just by their nature. So suppose you had a different problem where your function is, say, f of x equals cosine of, say, pi x divided by x. If you had something along these lines, then we could say f is continuous because cosine is continuous on the entire real number line, and x is continuous on 5 to infinity. So you can just assert what you know about the functions in question. Polynomial functions, trigonometric functions are always continuous and so on. And if you're not sure if the conclusion you have on part 1 is quite right, you're always welcome to just ask. Email is fine as well. Other questions so far with part 1? Okay, so we dodged the discontinuity at n is 5, giving us a continuous function. Next on condition 2, we need to check that the function's positive. But a lot of these are just going through the motions. On the domain from 5 to infinity, this would be 5. We're taking the square root of something that's always positive, then cubing it. So we'd always get a positive result. So if it's painfully obvious you have a positive function, then you could just say for part 2, f of x is bigger than or equal to 0, really strictly bigger than 0, for all x in 5 through infinity. So you don't really have to back that up. I mean, if you analyze the function and see that there's no possibility for it to ever be 0 or negative, then just assert it and that'd be fine. You don't necessarily have to prove every single statement. We would just go on to the next. Questions with that so far? Okay, then the interesting part is decreasing. This can take a bit of work, but one way you could reason out that it should be decreasing is if we're taking the square root and then cubing, then there's something that is effectively along the power of 3. Not exactly, but something that acts like a power of 3 in the denominator compared to a power 1, which means the limit of that whole thing should be 0 altogether. But let's try a different approach. Let's use the first derivative test to prove that this time, just as a valid third option for that. Any questions before we try it out? Okay, so we're going to check 3 by the increasing-decreasing test. Let's do f prime at x. If we get a first derivative that, say, is always negative, then we can say the function itself must have been always decreasing on the domain from 5 to infinity. So we'll take a derivative. Yeah, question?
What if the powers are the same in the
Numerator, denominator? That's a good question. So in this case, we have power 2. The square root here, this does not exactly work that way, is going to give us something like a power of 1, but with the power 3 there, we would have power 3 down below. If it looks like this, however, then the limit this time is going to be, let's see, I think this limit should come out to 1, which is still okay as long as it's decreasing to that value of 1, but that's going to tell us that we do have a problem in that case. And if that was the case, if we had, say, n cubed over n squared with the n cubed, or n to the power 3 halves, I would just use the ordinary test for divergence on this one and completely sidestep the integral test. So keep in mind, this actually could be something that happens in a problem where you may use the integral test because you're just in the section for it, but if this limit comes out as something not 0, say there's a no on this line of the flow chart where this is in Moodle, you can assert immediately that the series would diverge by the test for divergence. But this is the nasty option where now it's up in the air. The limit of this would be 0, which is a yes on the flow chart, which means the test has failed. It's directing us to try something else. What are the questions so far? Okay, so let's take the first derivative at x, work that out, which means we're taking the derivative of this thing, and that's kind of exciting because maybe that's the second time we've done the quotient rule ever. I'm not even sure at this point, but it's now a quotient rule. So let's revisit that. In the quotient rule, we can take the derivative of the numerator, that would be 3x squared, multiplied by the denominator, x squared minus 4 to the power 3 halves.
Erase the power.
Sorry, say again?
Power, the top power. Erase the power you added. There.
Oh, thank you, thank you. That's going to be a horrible problem, possibly. Just x itself, thanks. So if we take the derivative of the appropriate function, we would just get a 1 on the top, multiplied by the denominator, x squared minus 4 to the power of 3 halves. Thanks for that correction. That may not have possibly worked. Then we say minus, copy the numerator, which is x, multiply by the derivative of the denominator, which is a chain rule situation. First 3 halves comes down, which means the new power is 1/2, which converts it to a square root of x squared minus 4. But then we multiply it by the derivative of x squared minus 4, which is a 2x. Okay, so that's the numerator so far. Quotient rule is always a mess, so it is what it is. What should the denominator be?
Is it 2 times the denominator?
Close.
Denominator squared.
Exactly, yeah. So we take the full denominator, x squared minus 4 to the power of 3 halves, and just square whatever it happened to be. So that's the quotient rule so far. All we have to do is simplify and see what we get. So far, down below, we have x squared minus 4 to the power 3 halves minus, then we have to simplify all this stuff, but we have 2 canceling, so that's nice. Then here to here is going to be minus x squared, so minus 3x squared times the root of x squared minus 4. Down below, the power 2 cancels the power 2, or the denominator of 2, which was effectively a square root, and we get x squared minus 4 to the power 3. So we have to determine if this is always positive or always negative on the domain 5 through infinity. Any questions so far about that? So on the domain from 5 to infinity, is this always positive or always negative? I want to say always negative. Does that make sense why? One thing to take a look at is, if I put 5 as my lowest endpoint down below here, I'd get 25 minus 40 cubed. That's always positive. And as the value increases through 6 and so on, the denominator is always going to be positive itself. So the denominator is positive. Let's look at the numerator. If we put 5 right here, then I would have the power 3 halves of 25 minus 4. That would be the power 3 halves of 21. Minus, if I put it here, a 5, I would have 5 squared, which is 25 by 3, which is negative 75, multiplied by the square root of 21 itself, so power 1/2. So this is definitely going to be negative. Would you folks agree with that? And if I put in the value 6, it's more negative. So that tells me really altogether the whole thing is going to be negative itself. If I wasn't completely sure if that would be the case, we may have to do some factoring. But if you can tell by looking at what the domain is, the relative size of the subtraction in the numerator, I always have something smaller subtracting something larger, tells me the first derivative is negative. And here's our punchline. So f of x is decreasing since f of x, the derivative, is less than 0 on the domain from 5 to infinity. It's not always actually decreasing, but on that specific domain, it would be. That's a lot of work, so that's 1 through 3 so far, which means, hey, we can use the integral test. That's going to be our next step. Any questions so far to this stage? Okay, so once we check 1 through 3, then we can say that the next step is consider the definite integral from 5 to infinity. Once again, because we're starting at 5, that's where we'll check the convergence or divergence of this value, f of x dx, which means we're now taking the limit as t, a new parameter, goes to infinity, of the definite integral from 5 to t of f of x, which is x divided by x squared minus 4 to the power of 3/2 dx. So that's what we'll evaluate so far. Any questions with that setup? Okay, so we're back to the world of improper integrals. And to solve this one, it could possibly be something terrible. A trigonometric substitution may in fact work on this. And if you have to use a trigonometric substitution and a problem this long already, that really sounds bad. So there's got to be a better way, right? Anyone see the better way on this one?
You can just move the denominator up by making it negative.
You absolutely could, yes. We could say, instead of considering this, we could look at the limit as t goes to infinity of definite integral from 5 to t, x times x squared minus 4 to the power of negative 3/2 dx. And this is kind of an interesting situation because if we wanted the antiderivative of, say, x squared minus 4 to the power of negative 3, or let's make it a positive 3 dx, then the way we would solve this one is, well, we'd have to cube x squared minus 4, distribute x in, then we can get antiderivatives term by term. In other words, we could just multiply everything out. However, with this, we can't actually multiply everything out in a logical way until we get to 11.10. We'll find a way to essentially multiply that out using the binomial series. But at the moment, we're kind of stuck. So anyone see a different way to go then? It's still a good step to take, but we need still something extra. A u substitution would do the job, yeah. So if we go for the right u substitution, we'll be able to escape this problem and go on to the next. So what should the u be in this u substitution? Yeah, if we take x squared minus 4, then the differential would be 2x dx. Or if you prefer, you could call that a differential equation. That sounds fancy after doing chapter 9. The new differential equation is that 1/2 du is x dx. And that's precisely what we have in the integrand. We have an x dx here and here. So we can now say that this is equal to the limit as the parameter t goes off to infinity of, we have a half that we can pull outside the integral sign, which can also go outside the limit itself. So a half here. So 1/2 du takes care of the x dx. Then we will have u to the power of negative 3/2. Now we have to make a decision. We can either change the limits of integration now or just undo the substitution. Once again, that's always your call. Sometimes if you're doing many substitutions, it's best to change as you go. What would you folks do on this one? Should we keep the limits of integration or change them? Okay, so if we go to change, that means we're taking 5, we're plugging it into here. That'd be 25 minus 4 for a lower limit of 21, which will evaluate to the upper limit of a parameter t, which would be t squared minus 4. So that would be the change in the limits. And if you decide to not change the limits of integration, you'll notice that you'll still get a 21, you'll still get a t squared minus 4, and it still goes into the antiderivative. So you're doing the exact same work, just in a different order. But now we're ready to get antiderivative of u to the power of negative 3/2. Any questions first to that step? Okay, so with our new limits of integration, our constant 1/2, we now get 1/2 times the limit as t goes to infinity of, this will go up by 1 power, 2 over 2. So we'll get u to the power of negative 1/2 now. We'll multiply by the reciprocal of the new power, which is negative 2 over 1. And this portion, u power negative 1/2, is going to be evaluated from 21 to t squared minus 4. So that's the setup so far. And next, we're just going to evaluate that integral, or this antiderivative, at these values, and then take the limit. Questions first before we go to those steps? Okay, so next let's do the evaluation. We have what altogether let's say we can cancel these just to make life a little bit easier. Now we have -1, or just negative, of the limit as t goes off to infinity of, I'll go with brackets here, t squared minus 4 goes into u to the power of -1/2. That would be 1 over the root of t squared minus 4. Where I've done two things. T squared minus 4 has gone on the inside. This has given us a power of positive 1/2 in the denominator, which is just a root down below. Does that look all right so far? Okay, then we go minus, and we do it again. 21 goes inside the variable u, but it's written to a power of positive 1/2 in the denominator, so it's root 21 down below, and that's a limit that we can take. Then, at this stage, the only thing that depends on the parameter t is the variable t inside t squared. But the root of t squared, as t goes off to infinity, that would be, well, infinity, right? But if it's 1 over infinity, what would be the result of this whole thing in the limit?
0.
Yeah, it becomes 0 itself. We have something that's constantly 1. The denominator is growing without bound, getting ever larger and larger and larger. So in the limit, this whole thing is canceling to 0, and we have -1 divided by the root of 21, multiplied by this negative sign way on the outside, which is positive, 1 over root 21. So we can say altogether that this thing converges. So if we have an improper interval that's convergent, that means the original series must be convergent as well by the integral test. But questions so far to this step, after the convergence of the improper integral? Okay, one thing I should mention is the negative signs are always going to cause havoc in algebra, and calculus is no different. It was just lucky that this resolved to positive 1 over root 21. But in fact, by the condition number 2 that we checked, if the function is really positive, you should never get a negative result here. So that's a built-in little tiny check that's in here as well. If I got negative anything, it would tell me that I've definitely made some mistake, and to figure that out next. But now we can give our overall conclusion. So we did all this work to conclude the series. I'll just denote it by a sub n to refer to it as tersely as possible. What must it also do? Yes, the original series way over there converges by the integral test. So that's the result of the integral test. It is quite a lot of work sometimes, so it's a good test to not use all the time. If you can skip it, then my advice to you is skip the integral test whenever possible. But questions so far with that test? Okay, so this is another thing that the integral test gives for us. We have a new test, which is a direct consequence of having an integral test. It tells us the following. So this is a new theorem, and its name is the P-series test. So we have here the series summation as n goes from 1 to infinity of 1 divided by n to the power of p is called a P-series. What's very tricky about this is it kind of feels like a geometric series in some sense, and if it was written this way, summation as n goes from 1 to infinity of, say, something along the lines a times r to the power n minus 1, this one is the geometric series. And its determination of convergence divergence is all about the base r itself. However, the P-series, whether it converges or diverges, has to do with just p and nothing else. So the power is what's determining convergence. And we can say here, the series converges whenever p, the power, is bigger than 1, diverges whenever p is less than or equal to 1 itself. So that's the entirety of the p-series test. It's a very fast test in the sense that you really just have to look at the form of the series, determine if it's a p-series or not, that's part of the trick, say what the value of the exponent is, whether it's larger than 1, which is convergence, whether it's less than or equal 1 for divergence, and you're done. Just state the conclusion. So it's possibly the fastest test we have, next to maybe sometimes test for divergence is a spot faster. Any questions about that so far? Okay, so this is good to put the geometric series right next to it because the conditions for convergence and divergence of these series are similar and they feel like they have a similar form. So let's just write this as an extra thing to compare and contrast with. This is equal to a divided by 1 minus r whenever the absolute value of r, the common ratio, is less than 1. So if the common ratio r is less than 1, we have convergence down here. However, if the power p is bigger than 1, we have convergence in this situation. So there's a reversal of directionality, which is painful to me as well. I don't like that. But it is what it is. It's very important to keep those two things separate because their conclusions are essentially opposite in that sense. Any questions about the test so far, the p-series test? Okay, maybe one last comment. The proof for this test is by the integral test. And that's precisely what the book does. They take the integral of 1 over x to the power p, and they determine when that converges and when that diverges. And it looks like exactly at 1 is where we have something suddenly change from convergence to divergence, which is very interesting. So let's see what happens at exactly 1 itself, just for an extra idea on how the proof should go. We won't do the total proof because that takes a long time, and I'll refer you to the book. But questions so far? Okay, so let's look at 1 over n to the power p. When p is 1, because that's suspicious, that's the boundary condition, or the boundary case, where we suddenly flip from convergence to divergence. So let's determine the convergence slash divergence of the p-series with p equals 1. So p-series has this form. It's a summation as n goes from 1 to infinity of a sub n. So summation as n goes from 1 to infinity of 1 over n to the power of p, which is 1. So that's the form of this particular p-series where we set this to a value of 1. In other words, this is the summation as n goes from 1 to infinity of 1 over n, which is the harmonic series. We know from experience that this should diverge, and the book gives you one proof on how to do that. Let's do that in this particular situation, again using the integral test, just to take another look at why it diverges. So by the integral test, with f of x equals 1 over x, and we're kind of ripping through it a little bit faster rather than how we might do it as a homework problem. So let's just go through this quickly. Would you agree it's continuous? It's not, right? But it is continuous from 1 to infinity because we dodge a vertical asymptote. Would you agree it's always positive? Yeah, if we are only allowed to put values of x is 1 or greater, this is always a positive quantity. And it's definitely decreasing because the numerator is constant. And as x increases, the values get smaller and smaller and smaller. So this meets all the conditions of the integral test. I would write all that out if it was a standard kind of problem. But this is just a partial proof of this test so far. So by the integral test with this function, we would look at the definite integral from 1 to over infinity of 1 over x dx, which is the limit as t goes to infinity of the definite integral from 1 to t 1 over x dx. So we can apply the integral test to this specific p-series where p is equal to 1. The book will then do it when p is bigger than 1 and when p is strictly less than 1 to get the other two cases. So we're doing a third of the proof. When p is specifically 1, this can become the limit as t goes to infinity of the natural log of the absolute value of x. But if you wrote it this way, that's okay because our domain gives positive values for the input in the logarithm. So that'll be evaluated from 1 to t. Then, well, as soon as we do the evaluation, we get limit t goes to infinity of the natural logarithm of t minus the natural logarithm of 1, which is 0. And this portion would give us, what is a limit altogether? Sorry, say again? Yeah, exactly. The natural log grows without bound. We're subtracting 0, which is not enough to stymie the growth. So this is infinity, and we have something that's divergent. So our conclusion is that the harmonic series 1 over n also diverges by the integral test. Which means you can also say it diverges by the p-series test, specifically when p is 1, since that's a portion of that test itself. Any questions so far about that? So we finally proved the harmonic series must be divergent. But if the harmonic series ever comes up, it should be exactly in this form, and you can possibly have a different value here. So there's other tricks we'll mention later on. But if you have something of this form in your problem, you can always just say it's a harmonic series, and it's divergent. So that's the one series you don't necessarily have to give a test to. Or if you'd like, you could say it's a divergent p-series with p is equal to 1, which puts you in that case. Let's try some different problems. Any questions with this so far? Okay, so this is what the problems start to look like in the actual homework assignment. I think we have time to look at 2 interesting cases. Then we'll do some review problems when we come back on Wednesday. We'll also look at how to possibly estimate sums using this test. And for this one, with the same instructions, just determine convergence or divergence, let's consider as n goes from 1 to infinity of 1 over n to the power of, let's make it be 1.003. So this is really a problem you may see as a homework problem. To do this, what would you first say? Would you agree, for example, is it a p-series, really? Yeah, some say yes. Yeah, it absolutely is. The way to tell is, if the thing that changes, the index, is the base,
P is greater than 1, so.
exactly, so it's a p-series because n is the base. Then you said the p is 1.003, which is bigger than 1. So what's the conclusion? It must converge. Whenever we have a power greater than 1, we get convergence. We found here if the power is exactly 1, that would be divergence. And the remainder of the test says anything less than 1, in fact, including 1 itself, would be divergence as well. So this is a p-series, where this is the value of p and it converges. You could say by the p-series test, but if you said p-series here already, then that is kind of redundant. So I would say this is the minimal amount of work that you could do for a complete solution. They can be really, really fast. Really, most of the work is to determine, is it a p-series or is it a geometric series? But this is the feature of geometric series. The index n was the exponent down below, whereas now it's the base instead. Any questions about that one? Okay, maybe let's try a slightly different one next. Let's say we have the summation as n goes from 1 to infinity of this series. Let's make it be, how about n to the power of -3. Then the things I would look at on this one is n is still a base. It never appears as an exponent anywhere else. It doesn't appear as a coefficient. So we can say that this is still a p-series. What would you say the value of p is in this p-series? Is it 3 or -3? 3. Turns out it's 3, correct. The trouble with these things is they start to essentially just mess everything up. So it's our work to work with exponent laws, much like with geometric series, to figure out what the correct form should be. So I would take an extra step here and say that this is really 1 over n cubed, So that tells me that P is 3, which is greater than 1, so this converges as well. So that's essentially how these things start to go. They're really not too bad, as long as it's an actual bona fide P-series. If we do anything else, suppose it looked like this, then we cannot use the P-series test, at least not on its own. We may have to combine it with a comparison test, because it compares to something we know, 1 over n cubed, to be convergent. So that's essentially how these kind of problems go. We could do quite a lot of these pretty quickly. I think this might be a good stopping point. Any questions then before we call it a day? Definitely a good stopping point then. We only have less than a minute. So when we come back on Wednesday, we're going to pick up from here and look at some things we can do with this particular test as far as estimation goes. Then we'll start 11.4, which will finish on Thursday. So if you have questions, feel free to stick around. If I owe you an exam, then please come and visit me. I'll have it down below.